Welcome to the deep dive. You've sent us your notes and research on, well, one of the most fundamental challenges in modern computing.
Right.
How do we teach a machine to truly understand human language?
That's a huge question.
It is. We are diving deep into the engine room of AI today, focusing on what's called text classification and how we can, effectively measure something as messy as human emotion.
And text classification is pretty much what it sounds like. You're applying machine learning algorithms to categorize and interpret just massive amounts of natural language data.
Right.
This kind of foundational work, it's the bedrock for everything from, sorting your emails and classifying news articles to way more complex systems, things used in question answering and natural language inference.
But the task we're really focused on today, and it's the perfect case study in your source material, is arguably the most relatable one. It's about figuring out feelings. We are tearing apart the process of sentiment analysis.
Sentiment analysis.
Yeah.
It's often called opinion mining, and it's a specialized subfield of natural language processing, or NLP.
Okay.
Its core function is just to classify a document based on the underlying attitude, the polarity of the writer. Is that movie review positive or negative?
Is that customer service tweet expressing satisfaction or, frustration?
Exactly that.
And our sources, they use the huge IMDb data set. That's a collection of 50,000 pre-labeled movie reviews as our working example.
So we already know which ones are positive and which are negative.
Right. So our mission for you, the listener, is to walk through the 4 essential steps required to turn that mountain of raw, messy text into neat, clean, numerical features that a machine learning model can actually ingest.
We'll cover all the required steps. So rigorous text cleaning, translating words into numerical feature vectors,
And then training the classifier.
and then seeing how that classification power can be repurposed for a completely different task, like topic modeling. It all starts with the data.
Okay, let's unpack this, starting with just the sheer labor involved in prepping 50,000 documents.
Oh, it's significant labor. I mean, we often forget that something like 80% of data science is just data cleaning.
Right.
And when you're dealing with large text corpora, even just reading those 50,000 documents into a processing structure like a pandas data frame, that takes real time.
I can imagine.
Your sources note that even with tools like PyPrint running to show the progress, loading alone can easily take 10 minutes. And that's before you even start the cleanup.
So once the reviews are finally loaded, what are the priorities for cleaning? We need to standardize, I assume?
Absolutely. Standardization. It begins with converting everything to lowercase.
Okay, that makes sense.
And while this means we lose capitalization that signals proper nouns for sentiment analysis, the emotional tone is just more important than the specific entities.
Got it.
Then we use regular expressions, those tiny little programming patterns, to scrub out unwanted noise. Stuff like stray HTML tags, which are really common in script reviews, and most punctuation.
Okay, hold on. If we're purging all punctuation, doesn't that make the cleaning process a little too aggressive? Are we losing valuable information the writer wanted to convey?
That's a critical question.
Yeah.
And it leads to one of the most, I think, brilliant exceptions in the cleaning process. We have to keep emoticons. So while standard commas, periods, quotation marks, those are usually removed. But symbols like a smiley face or a frowny face, they're basically pre-labeled sentiment.
They're a direct signal.
It's an unambiguous signal of positive polarity. So we keep the face, but we usually remove the nose character, the little dash in the middle, just to standardize the token shape.
That makes perfect sense. They're features, not noise. So once we have these clean, standardized reviews, the next step is breaking them apart into usable pieces. Tokenization.
Exactly. The simplest tokenization is just splitting the text by white space. But we often go further than that to reduce the complexity and the size of the overall vocabulary. This is where word stemming comes in.
And stemming is the process of kind of hacking a word down to its conceptual root, right? Like turning running, runner, or ran all into the core word run.
Yes, exactly. The underlying meaning is the same, but if we don't stem, the model sees 3 separate distinct words, and that just increases the dimensionality of our final feature vector for no good reason.
So you consolidate related concepts.
By stemming, yeah, we consolidate. The classic simplest algorithm for this is the Porter stemmer.
And your sources mention others, like the Snowball and Lancaster stemmers within the NLTK library. So if we have multiple tools for this, why pick one over the other? Does that choice actually impact the final classification?
It can, yeah. But the choice is usually a trade-off between speed and accuracy. The Porter stemmer is simple, it's fast, but sometimes it's a bit too aggressive. It can chop words too short until they're almost unrecognizable.
Nice.
The others, like the snowball stemmer, they're slightly more refined, a little more context-aware. They offer potentially better results, but at the cost of being slightly slower. For a high-volume task like this, 50,000 reviews, we often just start with the simplest, most efficient method.
Okay, so once we have our standardized stems, we apply that final filter, cutting out the stop words.
Right. That's removing the linguistic scaffolding words like, is, has, and the like.
The connective tissue.
That's a good way to put it. These words appear with high frequency in every document, positive or negative, so they do absolutely nothing to help the algorithm differentiate between the classes. The NLTK provides a list of about 127 standard stop words for English. Removing them just drastically shrinks the size of our vocabulary without losing the sentiment-bearing concepts.
So that brings us to the biggest, this is the biggest conceptual leap. Machine learning models fundamentally only work on numerical values. How do we take the clean stemmed word disappointing and turn it into a number the computer can actually calculate with?
We rely on the bag of words model, the BO model. This is the standard foundational technique for representing text numerically.
Bag of words.
It treats the document as just a collection, a bag of words, where the order of those words is completely ignored.
So how does the machine build the numerical representation from that bag?
Okay, so first it extracts every single unique token, every word that survived the cleaning process, from all 50,000 movie reviews.
A whole set.
The whole set. This creates a massive master vocabulary. Then for each individual review, it builds a vector, which is just a list of numbers, where each position in that list corresponds to a unique word in the master vocabulary.
And for a single review, that vector must be enormous. A 500-word review might only use a tiny fraction of the, tens of thousands of unique words in the whole data set?
Precisely. And this means the resulting vector is extremely sparse. It's mostly zeros.
Right. This
is a crucial engineering detail. If you have a vocabulary of, say, 50,000 unique words, and a single review only uses 300 of them, 99.4% of that vector is just zeros. And that sparsity is vital for computational efficiency, for memory saving. When we scale this up to millions of documents, we only need to store the locations of the non-zero numbers.
And what are those non-zero numbers? What do they represent?
That is the raw term frequency. It's designated as 6 collars equals TFTI, TDR. It's simply the count of how many times a specific term appears in a specific document. In Python, you get this initial transformation using scikit-learn's count vectorizer.
Now, if we just count individual words, that's a 1-gram or unigram model. But a single word can lack important context. If I say, that movie was not good, counting not and good separately, you lose the meaning entirely.
You do, and that's where n-grams come in. To capture that crucial context, a relationship between adjacent words, we group the tokens into sequences.
Oh.
So a 2-gram, or a big gram for the phrase, the director was brilliant, would produce the director was and was brilliant. A 3-gram would capture 3 words in a row.
So the power of the n-gram is that it enforces a sense of order on the bag, even though the overall document word order is still ignored. It's capturing local context.
It is, yes. And this is controlled really easily in the count vectorizer, using the n-gram range parameter. For sentiment analysis, using bigrams is really common. It often captures important linguistic constructs like not great or terrible acting, which a single word count would just completely miss.
So here's where we hit the real puzzle, though. If a word appears frequently, it gets a high raw count, right?
Right.
But if the word movie appears in almost every single one of the 50,000 reviews, both positive and negative, doesn't that high raw count actually make it useless for classifying sentiment?
It does. It absolutely does. That word movie has no discriminatory power. If a feature is present in everything, it tells us nothing about the difference between the classes.
So how do you solve for that?
To solve this, we introduce the crucial refinement: term frequency inverse document frequency, or TF-IDF.
This is where we stop simply counting and start weighing relevance.
Precisely. We're building a weighting scheme that actively punishes common, non-discriminatory words while boosting the significance of words that are rare but may be very present in a few documents.
Okay, that's interesting.
You can think of PFIDF like a hire manager looking at resumes. The raw turn frequency, the TF part, is just the number of times a skill is listed.
Okay, so if every single candidate lists email, that's a high term frequency.
Right, but the inverse document frequency, the IDF component, that acts as the critical filter. It essentially says, if everyone lists email, that skill's less important. It gets downweighted.
I see.
It gets downweighted compared to if only one person lists, I don't know, quantum computing, even if they only list it once.
So it's about rarity.
It's about rarity across the whole collection of documents. The IDF component does this mathematically by looking at the total number of documents versus the number of documents containing that specific term, and then it takes the logarithm.
And the logarithm is key because it stops those extremely rare words from accidentally being overweighted just because they showed up in one review. It smooths the curve.
Correct. So the final text TF-IDF-TD score is that term frequency multiplied by the inverse document frequency weighting. This rescaling just ensures the resulting feature vector is highly, highly meaningful.
Can we look at the specific effect on a word? You mentioned the word is earlier as a stop word.
Let's use that example. In a raw count vector, a stop word like is might have a term frequency of 3 or 4 in a given document because it's just so common. If we only use raw counts, is contributes significantly to the final classification, which is, it's ridiculous.
Right.
But because is present in nearly every single one of the 50,000 documents, the IDF part of the equation becomes very, very small.
So you multiply the high raw count by a near zero relevance factor?
It's exactly. The final output, especially after L2 normalization, which scales the entire vector so its length is, one shows the weight of is, just dropping dramatically. In the source example, that word ends up with a final normalized score of only $0.4555 ounce, despite its high initial count.
Wow.
And that just shows the power of TF-IDF. It's focusing the model on the words that actually matter for sentiment, like terrible, fantastic, or mediocre.
So we've taken the raw text, we've cleaned it, stemmed it, stripped the stop words, converted it into a sparse numerical vector, and then refined those numbers using TF-IDF. This polished feature vector is finally ready to train the model.
Yes, and this brings us to the machine learning phase. So for the supervised sentiment task, the sources use logistic regression as the final classifier. But before that, we have to address the workflow. When you have so many sequential steps, vectorization, TF-IDF, transformation, normalization, training, you need a way to chain them together reliably.
That's where the pipeline class from scikit-learn becomes essential, right?
It's non-negotiable for production machine learning. The pipeline acts as a container, and it ensures that when new unseen reviews come in, they follow the exact same cleaning and vectorization steps that the training data followed.
So it's about reproducibility.
It's vital, and it also lets us easily optimize the parameters for the entire process using tools like Grid Search CV.
We've established how these polished numerical vectors allow the model to classify sentiment positive or negative. But what's really fascinating to me is that those same perfectly prepared vectors can be used for tasks that don't even have labels.
Now we shift gears completely. We go from a supervised task to an unsupervised one. Topic modeling.
Okay.
We're taking the same 50,000 reviews, but instead of asking if they're positive or negative, we ask, what are these documents about?
This is a type of clustering. So the machine is essentially grouping the documents based on which words frequently appear together.
That's the goal. Topic modeling is how massive, unlabeled archives, like the complete historical records of a library or a decade of public speeches, can be automatically sorted into meaningful categories. And the tool used here is latent duplicate allocation, or LDA.
LDA.
It looks for hidden, shared topic structures within the text.
And the results from applying LDA to the IMDb dataset, I mean, they prove how effective this whole numerical representation process is. The machine, having never been told anything about genres, successfully identified 10 very clear, distinct topics.
It's incredibly illuminating. Based purely on the numerical patterns of word co-occurrence, the LDA was able to group reviews into clusters that corresponded to, well, things like war movies, art movies, crime movies,
Horror movies, comedies.
movies related to TV shows, movies based on books, and even a cluster for just generally bad movies.
It's astonishing. The machine can identify something as specific as horror movies just because the word scream might appear near the word monster, but rarely near the word child, which conversely might define the movies about families cluster. The structure of human thought is literally embedded in those numbers.
It confirms that once you successfully translate the complex, ambiguous nature of human language into a clean, weighted numerical feature vector, the possibilities are, well, they're endless. That vector can answer a multitude of questions, both labeled and unlabeled.
So what does this all mean? We started with 50,000 lines of messy, raw text, complete with stray HTML. We learned that meticulous cleaning is everything, even down to preserving the sentiment value of a simple smiley face.
Right.
We then converted those cleaned words into sparse numerical vectors using the bag of words approach, and critically refined those numbers using TF-IDF, ensuring we prioritized context and punished overly common words like the or is.
And finally, those precise vectors were proven to be the key to both supervised tasks, like sentiment classification, and unsupervised tasks, like automatically categorizing genres. If we connect this to the bigger picture, this methodology, this precise four-step journey from word to number, it's the essential engineering required to classify, understand, and extract insight from any large corpus of text. This is how we move beyond simple search and actually get machines to interpret human experience at scale.
And think about the power of that final unsupervised step. If LDA can accurately categorize 50,000 movie reviews into clean topics like war and horror just by analyzing which words clump together, what hidden, unlabeled patterns could this exact process uncover in something truly massive? Like the entire global archive of corporate emails or a decade's worth of aggregated financial commentary.
Right.
The patterns are there, we just need the math to reveal them. That is something for you to mull over until our next deep dive.